So I'm the first of several speakers from ANSTO who are sponsoring this conference. So thank you to the ANA for inviting me. ANSTO has nuclear science and technology at its heart, and it operates several neutron scattering facilities and other large-scale infrastructure in support of nuclear science and technology. So it's a large government-funded organisation, and it operates over several campuses. The one that you're most familiar with is the Lucas Heights campus, but there's also the synchrotron in Melbourne, just outside of Melbourne, and the cyclotron just down the road in Camperdown. So at the Lucas Heights campus, we have what we're all most familiar with here, which is the 20 megawatt reactor, the Open Pool Australian Light Water Reactor. Now, as we know, the light water reactor is a multi-purpose reactor. It may be small, but it's mighty. It produces only 20 megawatts, but 50% actually now, I was surprised to learn, of the world's silicon for semiconductor industry through transmutation doping. So that's an outstanding achievement. It also produces radiopharmaceuticals, and we heard about that. And of most concern to me is the neutron scattering facility that it supplies neutrons to. So I'll tell you a little bit about that. So I work there as one of the instrument scientists, as Edward mentioned, and we operate a suite of neutron scattering instrumentation, and that gives us insight into what materials are at the atomic and molecular scale, which underpins what they can do and how useful they are in new technologies, in materials, and in industrial applications. So it's really important that we understand what a material is and how it works in order to create new materials or to make existing materials better. And that underpins our technology advancement. So I also have a position in support of this, a professorial appointment at the University of Wollongong. And I work predominantly alongside them to push the frontier of new battery materials and understand lithium-ion batteries predominantly and how we can make them safer, cheaper, and better, more generally. Okay, so our role in this research is, as I said, understanding what a material is and how it works. It's a really pivotal role in advancing technology and materials research front. So I lead a research group from within the Australian Centre for Neutron Scattering. It's called the Functional, got a long name, it's called the Functional Materials for Energy Systems and Devices Project. It started off as the Energy Project. Actually, it started off as Neutrons for the Hydrogen Economy Project back in 2009, and then we changed the name to the Materials Project, Energy Materials Project, and now it's got this longer name. And it's really about materials that do something and functional materials, and how we can, through gaining that understanding into what a material is, make a device and that material perform a function better. We can also, in engaging in this fundamental research, potentially uncover new ways to do things. So that is not just looking at an existing material and the way that we know something works, but discover entirely new ways, for example, to supply or store energy. And that engagement in fundamental research gives us the best opportunity to really revolutionise energy storage and supply and any technology that we engage fundamental research in. So it's a high risk, high reward engagement opportunity, but it's cheap. Fundamental research doesn't have to cost much. So the reason that we use neutrons in this research is because we have to. There's no other way to get that information. You can make an analogy with X-ray characterization methods, which are commonly used to understand what a material is, the way that atoms are arranged in a material and the way that they move, which impacts what a material can do in terms of its properties. But you really can't get the same information that you can by doing those experiments with neutrons. So a really good example and clear example of that is these images here, which shows a simple camera, an old style camera, not really anything like a modern camera now, imaged using X-rays, and then the same camera imaged using neutrons. And you can see very clearly there are some major differences in the information that you obtain using those two techniques. And the reason for that is because neutrons, don't have a charge and therefore interact predominantly with the nucleus of an atom. And that makes them very penetrating, so you can get through larger pieces of electron-dense material, like, for example, lead, which you couldn't penetrate with an X-ray beam, even a quite high-energy one. And it also means that the information that you get relates to the nucleus of the atom that's there, and not to just how many electrons are there. And that's critical for understanding many materials, many functional materials, particularly those used in energy storage and supply. If you think about hydrogen storage materials, and we talked about what was mentioned earlier, that hydrogen is an energy carrier and not a source of energy. But if you want to look at hydrogen, or indeed a proton, the best way to do that is to use neutrons. Okay, so we have a suite of instrumentation at the Australian Centre for Neutron Scattering, depending on exactly what type of information you want. So if you're looking at structure, how atoms are arranged in materials, if you're looking at very small length scales or very large length scales, you might choose an instrument that's tuned to get that exact length scale that you're interested in. Or you might be looking at dynamics, in which case you choose an instrument that has an energy range within the time scale of motion of atoms that you're interested in. So we have a range of neutron scattering instruments. We have specialist scientists that run those instruments, such as myself, who work with you to get that understanding. So if you came to the ACNS to do an experiment, you wouldn't expect that you would perform the entire experiment by yourself. You'd be working alongside an instrument scientist such as me to help really get the detailed information that relates to the question that you're asking best from that instrument. Okay, so one of the few materials that I've been looking at, I've got a couple of examples to give here, is lithium-ion batteries, and specifically the performance bottleneck within lithium-ion batteries, which are the electrode materials. So I think I counted today that I have 5 lithium-ion batteries just in my bag, 2 on my hand, 1 in my phone, and my laptop. And I suspect that most people here would have somewhere between 2 and 3 lithium-ion batteries. These are a ubiquitous energy storage device, and they've really revolutionised the way that we live. And they're not perfect. We can't check them in our luggage when we travel on an aircraft, because it's not safe to do so. There are still many opportunities to improve this product. So the first step in that is understanding what the material is and how it works. And as I said, the performance bottleneck, and indeed the cost bottleneck for lithium-ion batteries, are the electrode materials. So we start with what it is. So we look at the phase composition, so the materials that are in there, how the atoms are arranged just in the dry powder. And then we look at how it functions during use. And this second question is very difficult to answer because the lithium-ion battery is a complex material. So during use, what happens is you have electrons that are liberated from one electrode, and a lithium-ion battery is rechargeable, so you have 2 electrodes. And they travel around an external circuit, creating a current that we can use. And charge balancing lithium ions will migrate from within that electrode across the separator and membrane, and then are accommodated in the other electrode. And the reverse happens during charge. So the way that happens, and the way that these electrode materials accommodate those lithium ions, and the way they release them, underpin exactly the battery performance characteristics. So how many of those lithium ions can be incorporated underpin capacity, how quickly they can be shuttled between the 2 electrodes underpin rate capability, and how many times they can do that reversibly is your cycle life. We all know when we get our new phone and we charge it up, it lasts a long time, and then some period down the track you're carrying additional battery packs to support your phone use because it's suffering from capacity decay. So looking at the mechanism for this capacity decay and other performance problems is the aim of this research. Okay. Ideally, we'd also look at that during function, because you get a more detailed and correct answer if you study the material during operation, rather than just looking at a battery and saying, okay, well, this is what it is right now at this particular state of charge. Okay, so we've developed methods to do that, and shown here is the high intensity neutron powder diffractometer, affectionately called Wombat. All of our instruments are named after Australian animals. This instrument is the fastest of its kind in the world. This is really leading edge infrastructure that allows us to study the structure, the arrangement of atoms in an electrode material within a whole battery during use. And so it's really amazing technology, infrastructure that has enabled us to understand battery function and improve that. Okay, so typically what we do is we look at the performance output of the battery, in this case charge-discharge curve, so you can see voltage, and then we'd correlate that with the structure of that electrode material along the way. Now you can see for this particular material, during its typical operating range of 1.5 to 4.2 volts, you've got an arrangement of atoms that changes quite dramatically. And two of these are quite a different length scale, quite larger than some of the others. And that creates strain in the material. And that is a source of performance degradation, of capacity degradation in materials. So we really want to eliminate this if we can. So now that we know the points of the voltage curve at which these unfavourable structures form, we can simply reduce the operating window to 2 to 4 volts and then eliminate those structures and thus gain 25% better capacity retention. So even without making any changes to the material, we now know how we can use the material in a better way. So this informs operational improvement. Moving further, there is an electrode material that's recently been not recently, but it's been commercialised, and it's a titanium oxide based material. It is a zero strain material. It has less than 0.1% volume change over its operational range. However, it has poor rate capability. That means how quickly you can charge and discharge and use the battery is a problem. And that relates to how these lithium ions move into the material and move out of the material. And we can look at that in real time using neutron scattering. So here you can see this very light element, lithium, and its distribution within this electrode during use. And that gives us information about why we're getting this poor rate capability of the material. And so we can, in detail, look at the positions, the structural positions, the atomic positions within that material that lithium likes to sit at. And it was known that there are 2 particular sites that lithium likes to sit at. And a third was postulated but never really confirmed, and we were able to see that experimentally. And going further, we could get more information about the rate of movement of these lithium ions, which tells us about the core rate capability. So we could see that the rate of insertion of lithium was about half that of extraction. That tells us something about why the material is suffering, in particular on charge, why it's harder to charge. Okay, and we can relate that to one of those positions of lithium. And that particular position, this 16C crystallographic site, tells you about the ordering of atoms in the material. We could relate that to actually the zero strain property of this material as well. It turns out that when lithium moves into this particular site, it actually changes the response of the material from expanding to contracting because of interactions. And so you have this system where it's suddenly a higher energy cost to put lithium into the material because you have the host material, this titanium oxygen, responding to lithiation. And I know this is a lot of detail, but it really does explain both the zero strain property as well as the core rate capability of this material. And it's all because of the repositioning of the oxygen atom when you get to a certain amount of lithium in the electrode material. So this is really in-depth detail that you can't get from any other method. And it really underpins the next step, which is technology advancement through changing that material to make it, to improve it. Now I'm going to talk about not an energy material. We started off studying this class of materials actually as porous sorbents for carbon capture and storage and separation of other energy relevant gases. And we discovered that they undergo really large reversible compressibility. And so we decided to look at that instead. So I'm going to tell you about that in the last few minutes. So this material that we discovered has an extreme compressibility. It undergoes 30% volume change reversibly. And because it does this reversibly, it means it also remains crystalline, that is, it has ordered arrangement of atoms, which lends itself to high chemical and thermal stability, very sought after properties for high pressure equipment devices. And so this material is about as squishy as polystyrene, but it's chemically and thermally stable. Okay, turns out that there's not just one material here, there's a series of materials. And by substituting one of the atom types in this material, you can change that compressibility. And so you can influence directly the bulk modulus. This is really chemical engineering, but we wanted to know how this happens. The first thing we did was collect information using, again, Wombat, about the arrangement of atoms as a function of pressure. So here you can see the Paris Edinburgh cell, which is a high pressure device that squishes our material, and then you can see the corresponding neutron powder diffraction data just shown on the right there. And because we've got these sharp peaks, it means the material remains crystalline during that process. Once we know where the atoms are, we can then perform some modelling, atomistic first principles modelling. This is really important because it gives us the most information that we can get about the mechanism for this. But it's really important that we get our model right. So we start off with knowing where the atoms are, which we obtain from neutron scattering, and then we do some other neutron scattering experiments that confirm our model. Basically, this is the measurement of the vibrational density of states. It tells us which parts of the material, which atoms are moving more and which are moving less during that compression. And that tells us how soft or hard some parts of the material are and why we can influence that bulk modulus at the atomic level. From that, we can get the answer, which is lovely. So then we can see exactly what the material looks like under load. So this is looking at the position of atoms within the material as a function of pressure. And we can see that this part of the material remains rigid and part of it is soft and highly compressible. And the part that's soft undergoes a structural rearrangement that also results in a luminescence change. So not only have we discovered that this material is highly compressible and reversibly so, it also undergoes a luminescence change that lends itself well to pressure sensing. So this is a useful material for high pressure devices, but also for pressure sensing. Once we have an exact understanding of how that property arises, we can also chemically engineer from first principles of material because we know the energy cost and contribution of every atom in the system to that change in volume. And this underpins our ability to strategically design new materials with properties that are desirable. Okay, so as I mentioned, the Australian Centre for Neutron Scattering has a suite of neutron scattering instrumentation, and we're a publicly available facility for use, so you can come and use us for free through a merit-based system. We have calls for proposals twice a year. The other way to access our facility is by paying. So we have many commercial clients, and some pay for non-disclosure, and you can access our facility and then walk away with the data or some analysis provided with us, and we will keep that perfectly confidential. And then we have a very small amount of our beam time available for discretionary use, so our director can decide that something is particularly urgent. If there's a student thesis, a critical part of a student thesis that is necessary to access our beam time. And these are essentially the three mechanisms that you can come and use our facility. So please do so. Thank you.
Yeah, wonderful. Thank you, Vanessa. Does anyone have any questions? No.
Vanessa, that's the second presentation you've given that I've seen, and you always introduce some fantastic ideas to people like me. I'm going to ask a simple question. I hope it's not too boring. Why do lithium batteries explode?
Yeah, so you get a build-up of rather those lithium ions, instead of going back into the electrode materials, they deposit on the surface of the electrode material, and then you get metallic lithium that then builds up in a dendrite, punctures through the separator and membrane, causes a short circuit. You get your electrolyte releasing, and then.
So is it related to age?
It's related to conditions. So sometimes there are impurities in the battery that can, in the electrolyte, that can lead to a faster breakdown and therefore build up of lithium, metallic lithium. So it can be a point of manufacturing issue. And I heard one of the other speakers talk about recycling batteries, and that's really important because something like only 50% of batteries meet specification at point of manufacture and then have to go off to either be disposed or recycled, which is really important. So it can be a manufacturing issue, or it can be something to do with conditions. So temperature causes electrolyte to potentially boil depending on what electrolyte you've got, or solvents for the electrolyte. I'm happy to talk about that with you. Or you can look it up on the web. There's lots of amazing videos of battery removal.
Hi. Yeah. Is it possible to remove cobalt from lithium batteries? And if so, do you think that'll become like a dominant thing?
Yeah. So I mean, obviously resourcing materials for batteries, particularly lithium-ion batteries, and ANSTO has a project looking at alternative lithium extraction methods, but also cobalt. So yes, cobalt is recyclable from batteries. Cobalt is not only expensive, although I understand its price has dropped recently, but also toxic. So we're looking at many alternative chemistries that replace cobalt with non-toxic, cheaper alternatives like iron. But yeah, you can recycle it, and you should.
Thanks for the talk, Vanessa. You've got 14 instruments at the moment.
I think more now.
I'm just going to ask, how many, are there any new instruments planned for the next 5 to 10 years?
Yes, and actually the reactor itself has space on the exterior where we've got provision for a second hall to have a whole suite of new neutron scattering instruments. So the investment in neutron scattering in Australia is in the source, and the best use of the source is to build more instruments. Yeah, so you either have instruments up close and personal to the reactor face, which is an expensive use of the source spatially, but some experiments necessitate that up close and personal positioning, or you extract neutrons away from the source through neutron guides. And we currently have one neutron guide ball, but there's plans to build a second one out the back, and we have space to do so, and we have a plan